Continuing our discussion of the square parallel plate capacitor, in part C, suppose that before the slab is moved by this distance dx, here we calculate the change in the stored energy, the plates are disconnected from the battery so that the charges on the plates remain constant. Determine the magnitude of the charge on each plate and then show that when the slab is moved dx farther into the space between the plates, the stored energy changes by an amount that is the negative of the expression for du given in part B. Okay, so in this part C, first we need to calculate the charge on each plate. The charge is equal to the voltage that we apply multiplied by the C equivalent. So it is going to be epsilon 0 capital L V over capital D L plus kappa minus 1 X. This is our stored charge. So I've copied the equivalent capacitance from part A of the problem. Now, how much is the stored energy? So if I'm disconnecting the battery before I move the slab, the stored energy is the initial stored energy, which is 1 over 2 C equivalent V squared, 1 over 2 equivalent capacitance times the voltage squared, which is epsilon 0 capital L over 2 capital D L plus capital L plus kappa minus 1 X times V squared. And this is equal to the charge stored Q squared divided by twice the equivalent capacitance. Okay, now since I removed the battery, in the final configuration, final stored energy will be equal to Q squared divided by twice the new equivalent capacitance C equivalent prime. So if I write the change in the stored energy, U final minus U initial, it will be Q squared over 2 1 over C equivalent prime minus 1 over C equivalent. So this will be equal to because for Q I can substitute C equivalent times V here, this expression. It's going to be V squared C equivalent squared, that's Q squared over 2. Then I will have C equivalent minus C equivalent prime over C equivalent times C equivalent prime. And you can see that one of these C equivalents will disappear. It will get rid of the square on top. And I will find the change in stored energy, delta U is equal to 1 over 2 1 over 2 C equivalent V squared times. So now I'm going to find C equivalent minus C equivalent prime. So in the C equivalent prime, X is going to become X plus dx. So that's the difference between them. So C equivalent minus C equivalent prime will give me a minus sign here. minus epsilon 0 capital L kappa minus 1 dx divided by d times C equivalent prime. All right, so C equivalent minus C equivalent prime divided by C equivalent prime. This is this value divided by C equivalent prime. And what is C equivalent prime? It is the same thing. For x, I substitute x plus dx. All right, so that gives me minus epsilon 0 capital L kappa minus 1 dx divided by 2d. Here I have C equivalent divided by C equivalent prime v squared. And once again, let me write here explicitly what is C equivalent prime. C equivalent prime is epsilon 0 capital L over d L plus kappa minus 1 x plus dx. So in the limit dx goes to 0, what happens to this ratio? C equivalent over C equivalent prime is approaching 1. So for very small dx values, this limit in this limit it approaches 1, and I see that the change in the stored energy will be this quantity. So I can approximately say that delta U is approximately a minus V squared epsilon 0 capital L kappa minus 1 dx divided by 2d. If I compare this answer with the answer to part B, I see that it's the same thing, just this time with a minus sign. So I have shown that it is the negative of the expression for du given in part B. Now part D, if F is the force exerted on the slab by the charges on the plates, then du should equal to the work done against this force to move the slab a distance dx. Thus du is equal to minus f dx. Show that applying this expression to the result of part B suggests that the electric force on the slab pushes it out of the capacitor, while the result of part C suggests that the force pulls the slab into the capacitor. So here this figure shows what is happening as we insert the dielectric. So because of the new charges that are being induced on the dielectric, it's actually pulled in. So this figure shows that the force in fact pulls the slab into the capacitor. Now explain why the result of part B gives an incorrect answer for the direction of this force. This method does not require knowledge of the nature of the fringing field. Okay, so du, the change in the stored energy, must be equal to minus f dx. So if I substitute that for part B, it is kappa minus 1 epsilon 0 v squared capital L dx divided by 2d. This implies F is negative when dx is positive. That is to say, the slab feels a force that tries to push it out, right? Because this is minus f dx equals du. So if I do the same exercise for part C, if I write du is equal to minus f dx, that is minus kappa minus 1 v square epsilon 0 L dx divided by 2d. This time I find that the force F turns out to be positive, so the dielectric is pulled in. All right. And how can I explain this discrepancy between the results of parts B and part C? When connected to a battery, the system is not isolated due to energy transfer between the battery and the plates. So if you write du is equal to minus f dx, this implies that du plus f dx, which is the change in the mechanical energy, this must be equal to 0. But this is true only for an isolated system. This is not an isolated system when it is connected to the battery. It is connected to an energy reservoir in some sense. So it is allowed to exchange energy with the battery, and therefore this argument does not apply to part B, but it does apply to part C because we have disconnected it from the battery and we find the direction of the force properly. Okay, so in this exercise, after calculating the equivalent capacitance in part A and finding the change in the stored energy for a small change in the insertion distance for the dielectric slab, we have looked at the charge that is stored on each plate, Q is equal to Vc, and we looked at the change in the stored energy when we change the distance, insertion distance, by an amount, small amount dx. We found that the change in stored energy when the plates are disconnected from the battery before the change is done, so that the stored charge is constant on the plates. This is minus the change in stored energy that we have obtained in part B. And because when we insert this plate, the force exerted on the slab by the charges on the plates should equal to the work done. It should act such a way that the change in stored energy should equal to the work done against this force to move the slab a distance dx. So du is equal to minus f dx. This relationship is only correct if the system is isolated in terms of energy. So we see a manifestation of that if we try to write this equation for part B, where we find that the force comes out to be negative, so that the slab is suggesting that the slab is pushed out. But when we do it for part C, the force is positive, the dielectric is pulled in. In reality, as you can see in this figure, because these charges will induce charges on the two sides of the dielectric, it will be pulled in to the electric field in between the parallel plates. So this is the correct answer. And this applies when the system is not connected to the battery. When it is connected to the battery, it is not isolated. There is an energy transfer between the battery and the plates. And so the charges that are building up here will apply forces on these charges, and these charges can be transferred between these plates and the battery, and therefore this picture does not apply. So this picture only applies when there is no battery connected between the terminals, which means the system is isolated in terms of energy.